Every year, millions of people walk across the same patch of ground. They come to see the geysers. They watch the steam rise. They photograph the hot springs glowing orange and blue, and then they get back in their cars and drive home. Almost none of them realize they were standing on the lid of the largest volcano on the continent. Not next to it, on top of it. The famous geysers, the boiling pools, the whole postcard landscape of Yellowstone National Park, all of it sits inside the mouth of a sleeping giant. The reason the ground is so hot is that a vast reservoir of molten rock is sitting just a few kilometers beneath the tourists' feet. This volcano does not have a mountain. There is no towering cone like Fuji or Vesuvius. Instead, the eruptions that shaped this place were so enormous that the volcano collapsed inward and swallowed its own peak. What is left is a crater so wide you cannot see it from the ground. You can only see it from space. Scientists have a special word for a volcano this big. They call it a supervolcano, and they have found something unsettling about this one. 3 times in the deep past, it has erupted with a force almost beyond imagining. Each time it did something that a normal volcano simply cannot do. It reached across the entire planet, and it cooled the sky. So the question we are going to answer today is a simple one, and it sounds almost impossible. How could a single volcano in one corner of North America freeze the whole world, and the bigger question hiding behind it? If it has done this before, what happens if it wakes up again? Let's take a look. First, we need to understand what makes this volcano so different from the ones you already picture in your head. When most people imagine a volcano, they see a mountain with a hole in the top. Lava pours out, ash rises in a column, villages at the base are in danger. That is a real and deadly thing. But in the grand scheme of the planet, it is a local event. The damage stays close to home. Yellowstone is not that kind of volcano. To understand why, you have to look underground. Beneath the park sits a chamber of hot, partly molten rock. It is not a neat little pocket, it is colossal. The main reservoir of magma stretches for tens of kilometers in every direction, and beneath it sits an even larger, deeper body of hotter rock, feeding it from below. This is the engine. This is what heats every geyser and every steaming pool you see at the surface. And here is the thing about the crater on top. The Yellowstone caldera, the collapsed basin left behind by past eruptions, measures roughly 45 by 85 kilometers. Let that settle for a second. That is a single volcanic crater about 50 miles across. You could drop a major city into it and have room to spare. In fact, large parts of the national park sit inside it. That is why there is no mountain. A cone gets built up slowly, one modest eruption at a time. But when Yellowstone erupts at full strength, it does not build, it empties. It drains that enormous magma chamber so fast that the ground above has nothing left to stand on and the whole roof caves in. The mountain doesn't grow, it disappears into the hole. So how do we know this actually happened? How do we know it wasn't always just a pretty park with some hot springs? Because it left evidence. Enormous, planet-scale evidence spread across the rock record of an entire continent. Geologists have identified 3 giant eruptions from this system, and they can read them like layers in a book. The first and largest happened about 2.1 million years ago. It is called the Huckleberry Ridge eruption. It threw out roughly 2,450 cubic kilometers of rock and ash. Now, a number like 2,450 cubic kilometers means nothing to a human being, so let's make it real. Imagine the volume of material it would take to bury the entire state of Texas under about 3 meters of debris. That is the ballpark we are talking about. One eruption, one bad week, geologically speaking. The second big one came around 1.3 million years ago. It was smaller, about 280 cubic kilometers, but by any normal standard, it was still a catastrophe. And then, the most recent great eruption, about 640,000 years ago, that one is called the Lava Creek eruption. It released roughly 1,000 cubic kilometers of material, and it is the event that carved out the giant caldera the park sits in today. Now, to make sense of these numbers, scientists use a scale called the Volcanic Explosivity Index. Think of it like a Richter scale for eruptions. It runs from 0 up to 8. Each step up is roughly 10 times bigger than the one before. The eruption that famously buried Pompeii was around a 5. The eruption that blew the top off Mount St. Helens in 1980, an event that shocked the United States, was a 5 as well. To reach the highest rank, an 8, an eruption has to expel more than 1,000 cubic kilometers of material. There is even a nickname for that tier, a super-eruption. And Yellowstone has done it not once, but at least twice. That is what earns it the title supervolcano. Not that it is hotter or angrier than other volcanoes, it is the sheer, almost unbelievable volume of what it can release in a single event. But so far, everything I have described is about destruction near the volcano. Ash collapsed debris across a few states. That is terrifying if you live nearby. It does not yet explain the title. It does not explain how a volcano in Wyoming could reach out and chill the entire planet. To understand that, we have to follow the eruption up out of the crater and into the sky. Because the thing that freezes the world is not the part you would expect. Let's start with the obvious weapon, the ash. In 2014, scientists at the United States Geological Survey did something clever. They built a computer model to answer a very specific question. If Yellowstone had a super-eruption today, using today's weather patterns, where exactly would all that ash go? The results were startling, and not in the way you might guess. The area right around the volcano, the northern Rocky Mountains, would be buried under meters of ash. Enough to collapse roofs, bury roads, and make entire regions uninhabitable overnight. But the truly strange finding was about how the ash spread. In a normal eruption, wind carries the ash in one direction, and the deposit looks like a long fan pointing downwind. A super-eruption behaves differently. It pushes out so much material so fast that it forms what scientists call an umbrella cloud. Picture the ash column punching up into the sky and then flattening out at the top, like a giant mushroom spreading outward in every direction at once. It becomes so powerful that it actually shoves ash against the wind in all directions for more than 1,500 kilometers. The result is not a fan. It is a bullseye. Heavy in the middle, thinning out evenly in every direction, and in the model, the thin outer edge of that bullseye reaches almost everywhere. Millimeters of volcanic ash falling on New York City, on Los Angeles, on Miami. Cities on opposite coasts thousands of kilometers apart, dusted by the same volcano. Now, a few millimeters of ash on a distant city sounds survivable, and on its own it is. But volcanic ash is not soft, fluffy campfire ash. It is powdered glass and rock. It is heavy, it is abrasive, and when it gets wet, it turns into something like wet cement. It clogs engines, it shorts out electronics, it collapses power grids, it grounds every aircraft across the continent because even a small amount of it can destroy a jet engine in minutes. It contaminates water, it smothers crops across the most productive farmland on the continent, the American Midwest, the breadbasket that feeds a huge fraction of the world. So the ash alone would be one of the largest disasters in the history of the country. Agriculture in ruins, transport frozen, cleanup measured not in weeks but in years. But here is the twist, and it is the heart of the whole story. The ash is not what freezes the planet. The ash is heavy. It falls back to Earth within days, weeks, maybe a few months at most. Gravity always wins. Whatever damage it does relatively quickly, and then it settles. The thing that reaches across the entire planet and lingers for years is something you cannot even see. It is a gas. When a volcano like this erupts, it does not only throw out rock. It releases enormous quantities of a gas called sulfur dioxide, and this gas does something that the ash cannot. It rises higher, It punches all the way up into the stratosphere, the layer of the atmosphere that sits above our weather, above the clouds, above the rain that would otherwise wash it back down. And up there where nothing rains, the sulfur dioxide reacts with water vapor and transforms into a fine haze of tiny sulfuric acid droplets. Scientists call these sulfate aerosols. Picture an unimaginably thin veil of microscopic mirrors spread out across the top of the sky. That is the key, because those tiny droplets do exactly what a mirror does. They catch incoming sunlight and bounce it back out into space before it can ever reach the ground. Sunlight is the only thing that warms our planet. Dim the sunlight even slightly, and the whole surface begins to cool. And because that sulfate veil sits above the weather, the rain cannot scrub it out. It just hangs there, drifting on the high winds, wrapping itself around the entire globe. It can stay up there for years, in a truly massive eruption close to a decade. So now you have your answer to the title. This is how one volcano freezes the world. Not with fire, not even really with ash. It freezes the world by throwing a thin, invisible sunscreen across the entire sky, and then leaving it there blocking sunlight from every field, every ocean, and every city on Earth for years at a time. The volcano is in Wyoming. The shadow it casts falls on the whole planet. But this raises a fair question. This all sounds dramatic, but is it just a theory? Has a volcano actually done this to the world before? Somewhere we can point to and say, yes, this really happens? It has, and we do not even need to reach back to a Yellowstone super-eruption to prove it. We have a much more recent example, and it is small compared to Yellowstone. In April of 1815, a volcano called Mount Tambora erupted in what is now Indonesia. By Yellowstone standards, it was modest. It released around 100 cubic kilometers of material, that is, roughly a tenth of Yellowstone's most recent super-eruption. A tenth. And yet that one eruption changed the entire planet. Tambora threw a huge load of sulfur into the stratosphere, and that sulfate veil spread around the globe and cooled it. On average, worldwide temperatures dropped by somewhere between about 0.5 degree and 1 degree Celsius. That sounds tiny. It is not. A shift of 1 degree in the global average is enough to move the seasons themselves. The following year, 1816, became known around the world by a haunting name: the year without a summer. In June of that year, snow fell on New England. Frost killed crops in the fields of New York and New Jersey in the middle of summer. In Europe, cold and endless rain rotted the harvest in the ground. Grain prices exploded. Livestock starved because there was no hay. Famine spread across the northern hemisphere, followed by disease. Historians estimate that the cold and its aftermath killed well over 100,000 people. And remember, that was from a volcano roughly 1/10 the size of a full Yellowstone super-eruption. So we are not guessing. We have watched a volcano reach up into the sky and steal a year of summer from the entire planet within recorded human history. Yellowstone at full power would be operating in a completely different league. If you want to see that league, you have to go further back, to another supervolcano on the other side of the world. Around 74,000 years ago, a volcano called Toba erupted in Indonesia. This was a genuine super-eruption, releasing an estimated 2,800 cubic kilometers of material, even larger than Yellowstone's biggest. And some scientists have argued that Toba came close to changing the course of our own species. The idea, which is genuinely debated and not settled, is that the volcanic winter that followed was so severe that it drove early humans to the edge, cutting the global human population down to just a few thousand survivors. Now, it is important to be honest here. That human population theory is contested. Newer research suggests the cooling was uneven, with parts of the northern hemisphere dropping by as much as 4 degrees Celsius, while much of the southern hemisphere barely felt it. And many scientists doubt that humanity was ever truly pushed to the brink by it. So take the near-extinction story as a hypothesis, not a fact. But even the cautious version of the Toba story tells you something sobering. A single supervolcano cooled large parts of an entire hemisphere by several degrees for years. That is the scale of power we are dealing with. That is what sits under Yellowstone. So let's put the full picture together. If Yellowstone had a super-eruption today, the sequence would go something like this. First, the region around the volcano is destroyed outright, buried in meters of ash. Then the ash cloud spreads across the continent, coating farmland and cities from coast to coast, grounding aircraft, shorting out power grids, and crippling the food supply of one of the most productive agricultural regions on Earth. And then, as the ash slowly settles, the real, long, quiet disaster begins. The sulfate veil high in the stratosphere spreads around the entire planet and starts dimming the sun. Global temperatures fall, growing seasons shorten or fail. And because the aerosols linger for years, this is not one bad harvest. Scientists estimate that a Yellowstone super-eruption could disrupt the global climate, and with it, global agriculture for 1 to 2 decades. That is the true threat, not the explosion, the winter that follows it. A world that is a little bit colder, a little bit darker, and a lot hungrier, for years on end, everywhere at once. At this point, you would be forgiven for wanting to sell your house and move to the far side of the planet. So now we get to the most important question of all, the one everybody actually wants answered. Is it going to happen? Is Yellowstone about to erupt? And here, finally, the story turns, because the honest scientific answer is reassuring in a way the internet almost never tells you. You have probably heard the scary version. It goes like this. Yellowstone erupts every 600,000 to 700,000 years. The last big one was about 640,000 years ago, so the volcano is overdue, any day now. That sounds terrifying. It is also, according to the very scientists who study this volcano every single day, simply wrong. Let's take that logic apart, because it falls apart quickly. The claim that Yellowstone erupts on a schedule comes from averaging the gaps between its 3 big eruptions. But think about what that actually means. 3 eruptions only give you 2 gaps between them. 2. You cannot find a reliable pattern from 2 numbers. If you flipped a coin twice and got heads both times, you would not conclude the coin only ever lands on heads. And the 2 gaps are not even the same. The gap between the first and second eruptions was around 800,000 years. The gap between the second and third was closer to 660,000 years. Those are wildly different. There is no neat clock ticking down here. Volcanoes do not run on schedules. They erupt when the physical conditions underground are right and not one day before. So the word overdue does not even apply. You can only be overdue for something that runs on a timetable. Yellowstone does not. But the far more powerful reassurance is not about statistics, it is about physics. Because we can actually look inside the volcano, and what we see tells us it is nowhere near ready. Remember that giant magma chamber under the park? For a super-eruption to happen, that chamber has to be full of enough molten, mobile rock to erupt. Scientists estimate you would need the chamber to be somewhere around 50% molten or more to fuel a catastrophe. So how molten is it right now? Measurements suggest the main chamber is only about 5 to 15% molten. The rest is essentially solid cooling rock. It is not a churning cauldron of lava waiting to burst. It is mostly a hot, stiff, crystalline sponge. There is simply not enough liquid magma down there to produce a super-eruption, and getting from that state to an eruptive one is not something that happens overnight. It would take a very long time, and it would give us a lot of warning. Which brings us to the last piece of good news. We would see it coming. This is possibly the most closely watched volcano on the planet. The United States Geological Survey runs the Yellowstone Volcano Observatory, and the entire region is wired with sensors. Instruments track thousands of small earthquakes every year. Precise GPS stations watch the ground rise and fall by fractions of a centimeter as magma and hot water shift below. Satellites measure the swelling and sinking of the whole landscape. And here is the crucial point. A supervolcano cannot sneak up on us. Before an eruption of that magnitude, that magma chamber would have to fill and pressurize dramatically. That process would shove the ground upward in a big and obvious way. It would set off swarms of earthquakes far beyond anything normal. It would change the gases seeping out of the ground. These are not subtle signals. They would be screaming alarms, and they would build up over a long stretch of time, likely years, giving people the chance to prepare and evacuate. Right now, none of those alarms are ringing. The earthquakes under Yellowstone are the ordinary background rumble of any active geothermal area. The ground breathes up and down a little as it always has. There is no sign of magma gathering for a great eruption. So what are the actual odds? The United States Geological Survey estimates the yearly chance of a Yellowstone super-eruption at somewhere around 1 in 730,000. To put that in perspective, on any given year, you are far more likely to be struck by lightning than to witness Yellowstone blow its top. And even that number is probably too high for the near future because it comes from that same flawed averaging of only 2 intervals. The scientists who calculate it are the first to admit it is barely more than a rough guess dressed up as a statistic. So let's step back and hold both truths at once, because that is the real honest picture. Yes, underneath one of the most beautiful national parks in the world sits a genuine giant. It is real, it is powerful, and 3 times in the deep past it has erupted with enough force to throw a veil across the sky and cool the entire planet for years. The mechanism is real. The evidence is written into the rock of an entire continent, and we have watched smaller versions of it steal summers from the modern world. But it is also sleeping deeply. Its chamber is mostly solid rock. It is not overdue because it never ran on a schedule to begin with. It is watched every hour of every day by people who would see any awakening years in advance. And the chance of it erupting in your lifetime, or your children's, or their children's, is so small it barely registers. Which leaves us back where we started. Millions of people every year walking across the lid of the largest volcano on the continent, watching the geysers, photographing the hot springs. And now you know what all that steam really is. It is not a warning. It is the slow, quiet breathing of a giant that is, for now, and almost certainly for a very long time to come, still fast asleep. If you found yourself looking at the world a little differently just now, consider subscribing, and we will keep exploring the hidden forces shaping the planet beneath your feet.